I'd like to thank our co-sponsor societies, Computer Society, Circuits and Systems, and our SSCS chapter for sponsoring and organizing this event. I just go through a couple of announcements. We're starting a little late. It's mainly just regular announcements that I do every time, so I don't bother you again. For thanking our sponsors, especially Texas Instruments, for this great venue in great location. Let's have a round of applause for TI. And IEEE membership and the society memberships. There are many benefits, and you can find more information on IEEE.org to become members, and usually companies reimburse those membership dues. As for future seminars, in November we have Dr. Larry Nagel from Omega Enterprises. He's basically, he's well known for inventing a SPICE, circuit simulator, back in the 80s or 70s. And he's the recipient of 2019 IEEE Donald Peterson Award, which is going to be announced in ISSCC in San Francisco in February 2019. So we're really honored to have Larry for November. And in December, we have Dr. Danny Bankman from Stanford on a similar topic to tonight. Job openings, we've been trying to have like a web page and maintaining with folks for the job announcements. So Western Digital Research is looking for FPGA hardware engineer for machine learning. And you can contact Dr. Gunam, and also satellite communication startup Astronus. It's similar to SpaceX. They're also looking for FPGA developers. So you could contact them if you're looking for a job. And if you have jobs opening at the company, please contact us. Just send us an email or check out our website. As for logistics, we do recording for the SSCS Society. So we'd like to ask you to please switch off your cell phones, and also keep your questions to the end of the talk. So we're going to have running microphones so we can record your questions, unless the speaker would like to have it interactive. Now we get to the tonight's talk. It's my pleasure to introduce Professor Priyanka Raina from Stanford University. Actually, Priyanka, she had a talk at the Stanford System X Industry Alliance that I'm an industry member, so we basically got introduced, and then he later joined the Stanford in September. It was like back in March or April earlier this year. So we could invite her, and she kindly accepted the invitation. The talk will be on energy efficient circuits and systems for computational imaging and on mobile devices. And Professor Raina is an assistant professor in electrical engineering at Stanford. Previously, she was a visiting research scientist in architecture research group at NVIDIA. And she received her PhD from MIT, same for master's and bachelor's from IIT in India. Her current research interests are in the area of designing energy efficient and high performance circuits and systems for enabling computational photography, computer vision, and obviously machine learning. And it's focused on mobile and wearable devices, basically computing at the edge. And she was awarded the Best Student Paper Award at ECERC 2016, 2016 ISSCC Best Student Research Preview Award for her work on high dynamic range and low light imaging. Also presented in ISSCC 2013 and JSSC Journal in 2013. With that, and without any further ado, please join me in welcoming Professor Raina.
Thank you, Mujtaba, for the kind introduction. Good evening. My name is Priyanka, and today I will talk to you about my vision for how energy-efficient hardware accelerators will be critical to enabling a wide range of imaging and vision algorithms on mobile devices. In addition to that, I'm going to extend my observations to domain-specific architectures in general, since the techniques that I'm going to describe are not just specific to designing accelerators for image and video processing. They're also extensible to other domains such as neural networks or graph processing or security, etc. So I shall conclude the lecture with basically techniques that you can use when you go about designing your own accelerators for these applications. Okay, with that, let's get started. So who am I? I'm Priyanka. I basically just completed my PhD from MIT in January. I worked with Professor Anantha Chandrakasan, and my thesis was basically on the topic of the talk. Then I was a visiting research scientist at NVIDIA for about 7 months from January to August. And I basically joined Stanford a month and a half back as an assistant professor. So the topic of today's talk is going to be about imaging in video in general. And it's projected that more than 1.2 trillion photos will be taken in 2018. And 85% of these 1.2 trillion photos are going to be taken by cell phones, whereas only 10% by traditional digital cameras that you're used to. Moreover, the imaging that we do today with these cell phones isn't what it used to be 5 years ago. So today, the final image that we see is not merely a projection of light from a scene onto a sensor, but it actually results from a deep calculation. So for example, if a sensor captures a blurred image, you can actually computationally deblur it, meaning you can remove the shake and produce a sharp image and show it on the screen. However, when this deblurring algorithm is performed, say, on a mobile CPU, it takes on the order of 13 minutes to deblur one single photograph, which translates to 2,000 joules of energy. So now to understand how much 2,000 joules of energy is, if you consider a mobile phone battery, your phone will basically be dead after taking 10 photos. So that's the amount of energy it takes in executing these very complex algorithms, such as deblurring images after the fact, after they're taken. So my approach to solving problems such as these has been to design energy-efficient hardware accelerators targeted at these applications. So for example, in the case of deblurring, you can bring down the energy to about 0.1 joules per frame, meaning that now we can deblur thousands of photographs on our cell phone if we build a custom accelerator that does this deblurring. So the point is that accelerators such as these are not only critical to making applications faster, but actually enabling new applications to execute in mobile environments. Without this accelerator, you wouldn't be able to execute deblurring on a cell phone because of the enormous amount of energy it takes. So I'm going to give you like an application level highlight of the things that I have designed first, and then I'll go into some of the details. So to put things into perspective, let's first start by visualizing the implementations of different imaging and video applications. And let's basically plot them on this chart. So what's this chart? We're basically plotting energy on the y-axis and execution time, or how much time it takes you to process a photograph, on the x-axis, right? And both of the axes are on log scales. So basically, diagonal lines will be like constant energy delay product. So where do we want to be? We want to be somewhere down below in this bottom left corner, We want to have very low energy to execute an application, and at the same time, we want to do it very fast, so very low execution time. And if some application runs over here in the top right, in this red region, then it's basically unacceptable for a mobile device. Now, if you plot the application I talked about before, which was image deblurring, you'll see that that's where it lies on this energy and delay chart. And so with an accelerator, this is like the kind of order of magnitude improvement that you can get. So you can bring down both the execution time and the energy by orders of magnitude with a custom chip. Similarly, if you consider another application, for example, HDR or high dynamic range image, which today you find in most of your cell phones, the amount of energy it takes to do HDR in a cell phone on a CPU is over here. And when you design a custom chip, you can again get orders of magnitude improvement and bring it all the way down, right? Another algorithm that I looked at was motion magnification. So in this case, what your input is a video of a scene, and your output is a video of the same scene. It's just that the tiny motions in that video are magnified. So now you can use it for something like non-invasive health monitoring. Something like this will take like so much energy and execution time on a cell phone, on a processor, whereas by designing an accelerator, we can bring it all the way down here, okay? So the point of the slide is that you are able to achieve orders of magnitude improvement in energy and time by designing these accelerators. And we'll go about in the rest of the talk seeing how we achieve that and what are some of the key techniques that are used. So this is, so far I talked about like image processing type of applications, but this is equally true for applications such as image understanding, which are basically done using neural networks. So for example, if you consider something like object detection or scene classification or face recognition or captioning and so on, all of these are basically implemented using neural networks. And again, using custom chips, you are able to bring the energy and time much lower than what you would have for cell phone or even GPU implementations. Okay. So here's sort of my PhD in one slide. In the course of my PhD, I worked on designing custom chips for a bunch of different applications. The first one was deblurring of images. The second one was reconfigurable computational photography chip, which could do applications like high dynamic range imaging, low light imaging, glare reduction, and so on. And then the third chip was about motion magnification. So in all these three chips, we could achieve about 3 orders of magnitude lower energy, basically by designing custom accelerators. So with that, let's basically go deeper into the design of one of these accelerators. I won't have time to go into each one, but I'll pick one, and I'll show you the kind of techniques that you have to use when you go about designing accelerators such as this. Okay. So the first chip is about removing camera shake blur. And camera shake blur is basically the leading cause of blur in cell phone camera images. So basically the point is that when you're taking the photo, your hand shakes, and it leads to a blurry image. Now this is especially unfortunate when you don't have the opportunity to recapture the photo and basically the moment is lost forever. And so we would like to do something about it. So to understand what we can do about it, let's take a blurred image. So for example, here's a blurred image, and it has been corrupted by this camera shake blur. To deblur this particular image, basically to get a sharp image back, what one needs to know is the trajectory of the camera when the image was captured. Basically, you have to know how the camera moved when you were trying to capture the image so that you are able to undo it. So now this trajectory of camera is called the blur kernel. So in this particular photograph, you can actually see the blur kernel. In general, it's very hard to infer this blur kernel visually, but in this particular photograph, we have these point sources of light. And the point sources of light basically trace the trajectory when your hand moves, and so you're able to visualize it. And in general, you can't. So this is the kind of, these are the kind of kernels that we are trying to determine from these images. So in general, you can't infer them visually, so you have to infer them algorithmically. And so essentially, the problem that you're trying to solve is that you have an input blurred image, and to deblur that, what you do is, one, you algorithmically estimate this kernel. The kernel was the motion of the camera when you took this image. And then once you have the kernel, basically the blurring problem is modeled as a convolution between the blur kernel and the sharp image. So to recover the sharp image, your problem is essentially of deconvolving. So once you have the kernel and you have the blurred image, you can do a deconvolution to get a sharp image. Now, when you look at the runtime of this application, you find out that 99% of the time, computation time is basically spent in inferring what this kernel is, and then the deconvolution, once you know what the kernel is very fast. And so in this work, basically, our kernel estimation was a target for acceleration. So now, if we go one step deeper into what this kernel estimation entails, there are many approaches to kernel estimation. But there's this one technique called expectation maximization, or EM, based kernel estimation, which is very accurate. However, the problem is that it's also very computationally intensive. Now, the problem with using simpler techniques for kernel estimation is that if your kernel is not very accurate, you get all of these, when you do the deconvolution, you get a lot of ringing artifacts in your final image. So it doesn't look visually pleasing. So you want a very accurate kernel, but then you have to pay the price of doing a very computationally intensive algorithm. So let's look at how this algorithm works. So I'll give you like a big picture understanding of it, and you will be able to see what are the kind of computations that are there in this algorithm, and then how do we go about accelerating those computations. So for a big picture understanding, basically we are trying to solve this problem. We have a blurred image, and we want to decompose it into a convolution between a kernel and a sharp image. But the problem is that if we had either the kernel or the sharp image, you would be able to infer the other because it's deconvolution, but you basically don't have either of them. So where do you start? So where do you start? You basically start by guessing a kernel, right? Now, this kernel might not be the best possible kernel, but it's a start. So you guess it, and then you say, if this were my kernel, then what would be the sharp image? So you use this kernel to deblur your blurred image and get like a candidate sharp image. And you call this the E step. The names are irrelevant. You call it some step. And then essentially what you do is once you have this sharp image, you can infer a refined version of this kernel. And the reason you don't get the same kernel back is that you enforce some extra constraints on this problem. So you try to enforce constraints such as the kernel, the sharp image that you have has to obey certain characteristics. So for example, it has to be mostly flat with some sharp edges, which is what naturally occurring images look like. So basically, you'll have to trust me on this. When you do the second step, you don't get the same kernel back. You get a slightly more refined version of this kernel because of some extra constraints that you enforce in the optimization process. And this is called the M step. And so now you have a refined kernel, so you do it again, you get a better sharp image, and then you basically do it a couple of times until you get your final image, okay? And as I said, it works out because you enforce some constraints or regularization based on the characteristics of naturally occurring sharp images in the world. Okay. So now, so far so good, but what is the actual compute that's happening when you're doing all these steps? So basically, if you look at the algorithm, it's basically so this inherently looks very sequential, right? You get a kernel, then get a sharp image, then get a kernel, then get a sharp image, extremely sequential, with a lot of like nested loops. So you can't really do like data parallelism like you do in neural networks, like basically send different data to different processors and just get speed up by basically just exploiting data parallelism. You can't do that because the problem is inherently sequential. So essentially what you have to do, you have to extract the parallelism from the inner computation in both E step and M step. So you have to extract parallelism from the matrix operations that are there to reduce the execution time. So where did the matrix operations come from? So basically, when you represent your image mathematically and you represent this kernel mathematically, it's basically a matrix of some values, and each value corresponds to, like, say, for example, the intensity of the pixel. And similarly, in a kernel, it's also basically a matrix of values. So essentially, the computation that you're doing are some matrix manipulations on these large image and kernel matrices. Okay? And the other thing is that you can optimize, since being sequential is not necessarily a bad thing, because then you can share arithmetic units in memory between different stages that are not happening together. So you can share some resources between E step and M step. The other problem is that it requires a lot of memory accesses. And so essentially what we do is we have a lot of memory accesses, but those accesses are correlated in space and time. So basically by caching a lot of the data that's going to the memory with a buffer that's on chip, you're able to reduce the memory bandwidth and a lot of energy. Okay. So this is techniques at a high level, but let's go into like one specific problem inside of the algorithm that we can actually look at in greater detail. So here's the big high level overall architecture of the chip. It's complicated. There's a lot of blocks going around. There's solvers like optimization solvers, like conjugate gradient solver. There's some FFTs going on. There's some image correlation happening, another solver. So there's a bunch of steps because essentially you're trying to solve for the best kernel given the image and then solve for the best image given the kernel. So you have some basically iterative solvers inside the algorithm. Now I have limited time, so I'm not going to go into each of the solvers. But what I'll do is I'll talk about one such solver. So let's talk about this M step and let's talk about these two problems. So one is that of image correlation and one is that of implementing this gradient projection solver. And we'll just look at a couple of steps inside this algorithm. So the one thing that you need to do essentially in this particular algorithm is that you're basically trying to solve some sort of a minimization problem. And you can see that if you look closely, when you're solving for the kernel, so if you look at the equation for the M step, you're trying to determine the best kernel given some cost function. And that cost function is dependent upon the blurred image and the sharp image. And this matrix A for the cost function is basically determined by correlating the image with itself. So your S is your image. You take your image and you move it. You multiply, accumulate all the pixels. You take your image, move it by some other amount, multiply, accumulate all the pixels. So that's the kind of computation that's going on. We don't need to understand like the details of where it came about and how the math works, but that's what we are dealing with. So we're dealing with an image and correlating it with itself. So image, moving it along X and Y, and multiplying and accumulating the pixels. So that's the compute, okay? So what can we do about it? Okay. So to give you a better understanding of what this correlation computation is, let's just walk through a dummy example. So to correlate, to compute this, basically this correlation matrix, let's go back. So to compute this matrix A, in this case, this dummy 9 cross 9 matrix is my matrix A. So to compute any one pixel in this matrix, what do I need to do? I need to take my image. I need to move it by some amount, 1 cross 1, because there's a 1 cross 1 on the y-axis. Then I need to move it by some other amount, in this case, 0 cross 1, because that's on the other axis. And then I want to multiply and accumulate them and figure out what the area of this orange rectangle is. So that's the compute. Okay? But if you do it for every pixel, so this is what you want to do, but if you do it for every pixel, you're going to realize that the computation time is very large. So it's order m to the 4 n squared, where n squared is the number of pixels in the image. So if it's an n cross n image, there's going to be n squared pixels. The correlation matrix for an m cross m blurred kernel is an m squared cross m squared matrix. So for a 3 cross 3 kernel, this is a 9 cross 9 correlation matrix. And so there are these m squared times m squared entries, so many entries, so m to the 4 entries. And for each entry, you want to do n to the 2 computation. So it's a lot of computation, basically, right? So now what do? Okay? So the first kind of tricks while you're implementing these accelerators is basically don't do anything that you're not required to do. So basically, if you can skip any computation, you skip that computation. And this is a technique which is very commonly used in neural networks too. For example, if there's zeros, don't multiply by 0 if you know it's a 0, right? So that's what we'll get at. But where is the redundant computation? So the challenge is figuring out where is this redundant computation. So for example, in this case, what happens is that if you look at the diagonal entries of the correlation matrix, you'll see that the relative shift between these images is the same when you move it. So basically, what that amounts to is that the same pixels in the image are getting multiplied. It's just that for different yellow pixels, I'm taking the summation over a slightly different area of the image. So the first rectangle is shifted towards the right, then it's slightly shifted towards the left, and then more left. But most of the pixels are the same. The multiplication is the same. Addition is also the same. It's just that there are some tiny slivers that are different, right? So we apply our principle. Don't do any computation that you're not required to do, okay? So essentially, what you can do is that you can do the multiplication once, compute what's called the integral image of that product, which is basically you compute the multiplication and then you sum over, like you do a running sum over the rows, then you do a running sum over the columns. And then you can basically compute all these in like constant time from that one integral image, right? And you can trust me on this. It'll work out if you actually write it down, okay? So basically, what we realize is that by using techniques such as this, by discovering places where you can basically cut computation, you can improve something from m to the 4 n squared to m squared n squared. When you actually plug in values of m and n, you'll realize that it's actually a 42x speedup over what was there before. Okay? Now you can do better, okay? Now, if I were on, since I'm building hardware, I have the flexibility of doing things in parallel, right? Like that's the advantage of building custom hardware. So you don't have to compute each of these diagonals independently. You can have multiple, in this case, processing elements or PEs that are working on these different diagonals, okay? But then the question is, all of these diagonals are basically needing this image from the same image buffer. So then how do you deal with feeding? So point number 2, once you decide that you want to parallelize something, you have to also figure out how do you feed those parallel units, because otherwise they're just sitting there idle, right? Okay. So how are we going to feed these parallel units? So we realize that they are actually, in this case, it's easy to feed them because they're working on consecutive diagonals. So which means that you can have some sort of buffering or shift registers in the middle, and that will let you read in the pixels from the image buffer once and just sort of shift through in these different processing elements. Otherwise, you would need 6 ports on your memory, and that will just be too big. Okay. Right. There are some details on tiling for when the bank addresses collide, but we'll skip over that. Okay. So basically now with parallelism and with the mechanism of keeping all the parallel units busy, you can get basically with 6x more P's, you can get 6x improvement in your throughput. Why 6x? Why did not I go 100x? Because then it will get limited by something else. So then it will get limited by the amount of DRAM bandwidth that I have coming on the chip. So then if I go more, I'll have my PEs sitting idle while waiting for the DRAM. So like point number 3. Again, like a reiteration of point number 2, you have to keep your hardware busy. Okay. Okay. So now we have our correlated large A matrix. Now we can solve that original optimization problem that we set out to solve. Okay, so here's the problem. These A's and B's are coming from that correlated matrix. Okay. And so essentially what you do is you run some sort of an iterative optimization solver. It has these 2 steps called Cauchy point computation and conjugate gradient refinement. But we'll not go into what those mean. We'll just focus on figuring out what the compute is. So while you're doing this computation, solving this optimization problem, the most computationally intensive step is basically multiplying with this large A matrix. So first you spent a lot of compute in calculating this A matrix. Now you have to multiply vectors with this large A matrix. So again, we need to do something about it because that's mostly computationally intensive. Okay, so essentially the kind of compute that we are looking at is that you have this large A matrix and you have some vector x, which is somewhere in the middle of this optimization problem. It's some intermediate vector. And most of the compute is basically going into doing A times x equal to y. And you do it over and over. It's an iterative solver. So you do this multiple times. Okay. So we'll go back to principle number 1. Where can we cut computation, right? We have this A matrix. We have these new x vectors. Seems like there's no way we can do anything about it. But what we realize is that now it's an iterative optimization. So what we note that is that this x vector, in each iteration, it does not update all the time. Like all the entries don't get updated. It may be that the first entry gets updated or the first and the 5th entry gets updated. So there's some kind of sparsity in the number of updates that are happening to this x vector. And so we take advantage of that. In this case, what we can do is that, for example, if only the first entry of this vector changed, for example, x1 became x1 plus delta x1, and you already have y computed from a previous iteration, you don't need to read in the entire A matrix and multiply with this entire x. What you need to do is you just need to read the second column of A, or in this case, the first index 1 of A, multiply it with this delta and update your y, and you'll get your results matrix. If there's multiple entries, you do this a couple of times, and essentially what you end up doing is you end up reading only a few columns of A rather than the whole large A matrix. And so basically you're trying to exploit some kind of sparsity which is inherent to the algorithm. Like this is not true in general. It is true only in this case where we have these sparse updates. A similar kind of thing is also used in neural networks. They exploit basically some sort of sparsity that is inherent to that computation and not true in general. Okay. So again, we are able to reduce computation. We are able to avoid work that we don't need to do. Okay. So we, again, save another 11x in compute and memory when we do this. So that's great. And then there's some extra stuff where, because these are iterative algorithms, you can do some sharing and reduce area. But that's a minor point. Okay. So that's not everything that went into this chip. A whole bunch of other stuff went into this chip. But I just wanted to get some points across in terms of what kind of things that you can look at when you think about optimizing these algorithms and figuring out where to cut compute, and like these are the kind of things that appear, they appear generally, but you have to find those specific ways to implement them in the application that you have at your hand, because it might be different. The sparsity can manifest itself in different ways, or the redundant compute or the zeros can manifest itself in multiple different ways, and you have to find it, basically. So I built this chip. I taped it out in TSMC 40 nanometer CMOS, and here's the customary table, ISSCC table. And it does pretty well. So let's see how well it does. So I built the chip. I built the whole board around it. Basically, I built a daughter board that would plug into an FPGA, connected into a computer, fed and blurred images to see if I can produce kernels, and I can produce sharp images with those kernels. And so it worked pretty well. So I took this blurred image. This is a magnified small portion of this, and then my chip determined that kernel, and then I deblurred it, and it did pretty well. And similarly, there's another image, and it determined that particular kernel, and it worked pretty well, okay? And this is something that I iterated on earlier. We get orders of magnitude improvement in runtime and energy, so we do pretty well. And you can also do things like voltage scaling, et cetera. You can reduce energy even further by sacrificing on speed and stuff. You can also do trade-offs, right? So for example, you realize that it's an iterative algorithm, so the more number of iterations you'll run it for, the better your results will get. But so you'll get the best results in, say, 10 or 15 or 20 iterations, but maybe the results from iteration 6 are not that bad. So if your runtime and energy basically scale linearly with iterations. So in an energy-constrained environment, the hardware will allow you to basically stop early and cut down on your energy or time. You can also do this trade-off with like kernel size. So for example, instead of doing this estimation on the whole image, you can do estimation on a smaller image, determine the kernel, upsample the kernel, and do the deconvolution on the full image. The results will not be the same as determining a bigger kernel or determining the kernel on the full image, but it might still work out. So you can also use these trade-offs to basically trade quality for time or energy. Okay. So summary. I talked about some of the techniques already, about basically not doing redundant computation, exploiting sparsity and stuff like that. So basically reusing computation either statically by figuring out what's not necessary, and dynamically by seeing if the updates are sparse and so on. You can exploit hardware sharing in cases where your hardware is not being used all the time, so you can time multiplex it to make sure that it's used all the time. I didn't really talk about memory management here, but there's a whole bunch of on-chip scratchpad buffers which are caching the results so that you don't have to go to memory that often, otherwise you'll basically become memory bound. So we do pretty good. We get about 3 orders of magnitude reduction in energy and about like almost 100x reduction in runtime. Okay. So that was example 1. I'll quickly walk you through example 2. Which is slightly different. So in example 2, essentially what we are trying to implement is this type of filtering called bilateral filtering. And essentially what it is that you're all probably familiar with Gaussian blur. Gaussian blur is like, I'm a pixel, I'm going to get averaged with all of the pixels around me, right? But in bilateral filtering, what happens is that if I'm a pixel and the pixel sitting next to me is very different in color or intensity, I'm not going to average myself with that. I'm only going to average myself with my other neighboring pixels with which I have less of a difference. So essentially what it ends up doing is that it ends up removing the noise, but preserving the edges in the image. So there's an edge this is like an edge in the image. This is yellow, I'm green, and I want to preserve this edge, whereas this is not an edge. I want to blur over this. Okay, so that's basically what bilateral filtering is. The problem with bilateral filtering, the Gaussian filtering is cool because you sort of have the same convolution kernel everywhere you step on the image. Whereas here, I have one convolution kernel here, which is basically cut off from this side, but if I move over here, my convolution kernel is the whole thing, right? So you have different kernels at every point, right? So that makes it very hard to, for example, take an FFT and like do very fast convolution. Okay. So the way you implement, the way you make it slightly faster is basically by cheating. So essentially what you do is you take your image and you break it down into some blocks. So you block it off. And then what you do is you compute like a histogram of intensities in that block. So for example, on the right-hand side, I'm making this intensity histogram. Essentially what I'm doing is that in this area, I have 2 gray pixels, dark gray pixels. I have 3 light gray pixels. I have 1 very light pixel, and I have 2 white pixels. So I'm making this histogram of intensities. Along with the total intensity value. So I basically take this 2-dimensional image, and for each of those squares that I have marked off, I create this histogram along intensity. And what happens here is that, and you do this for all pixels, so now you have this 3-dimensional structure. And so what happens is that if these 2 pixels, which were very close to each other in the original image, end up very far away in this histogram image. And so what you can do is now that if you do a normal blur on the histogram, that blur will not mess up the top and the bottom pixel because they're far away. And then you have some transformation to go from that histogram back to the image. You now have a problem where you have a uniform kernel. So on that histogram, you can work with a uniform kernel. On the image itself, you cannot work with a uniform kernel. Okay? Once you can work with a uniform kernel, then life is great, basically. Right? So you basically create this grid. Then you can basically do a normal Gaussian kernel on this grid to get the convolved result. And then you have some way to go back to the original image. You do some sort of an interpolation to go back from this 3D space back to the 2D space. Okay. Never mind the details, but I'll point out what the takeaway is. So when you implement this, for example, convolution, and this is true for a lot of image processing applications, when you implement some sort of a kernel that's being applied on an image, essentially the type of processing that you do is that, for example, for a 3x3 kernel, what you end up doing is that you end up buffering 2 rows of image. Okay? And then once you start getting the 3rd row, you sort of have enough to start applying your kernel to. And so you start applying your kernel to the pixels on the right, and then as new pixels in the 3rd row start coming in, you basically slide your kernel. Basically as you do in convolution, just that the point to note is that you only need, for a 3x3 kernel, you basically only need to buffer 2 rows. And this is a general principle. It's called like, this template is called the line buffer, and most image processing applications have basically these line buffers. And the size of the line buffers depends upon the size of the kernel that you're using, right? So in this case, our filter was at the very edge, then it moved a little, and then it keeps moving a little, all the time. And so you can have cascades of these line buffered pipelines, okay? So this processor basically implements this line buffered pipeline. There's this bilateral filter that we talked about, where you create the grid assignment basically creates this grid. Convolution engine does this convolution in this line buffered way, and then there is some grid interpolation that goes back to the original pixel. Okay. So the point I want you to take away from this is not necessarily the results, but just the fact that in image processing pipelines, there is this line buffer template, and I'll come to line buffer templates later. Okay, so I implemented this chip, also in TSMC 40 nanometers, also put together a demo for it, and then the bilateral filtering kernel. So the bilateral filtering engine itself is used in a bunch of different applications. HDR is one application. So the core of HDR processing is this bilateral filtering that we just talked about. So you can implement, in this case, we implemented a bunch of helper blocks that would let us use the bilateral filter in combination with those helper blocks to basically do full HDR. So we did this HDR imaging. And we also did this low light imaging, where you combine images, a flash image and an ambient image together to get the details from the flash and the ambience from the non-flash image. So the core kernel in this is also this bilateral filter. And we did pretty good. So we got a 300x improvement in energy. This is compared to a mobile processor, which is already low power. Okay. So remember, what I asked you to remember was this line buffer. These line buffers are essentially, you can think of them as sort of caches, but like managed caches. They're not caches in the sense, like I'm controlling what happens in that cache. It's not like software control or something. So basically, most of the energy improvement comes basically from these caches, because you don't basically end up going to the DRAM for these. Every time you want to work on these pixels, you have them locally cached, and you have this moving sliding window on this local data. And so that basically leads to very efficient, energy efficient implementations. So with that, I will talk a little bit more generally about domain-specific architectures. So I believe that the future is about building ASICs, but building ASICs with some programmability, a little bit of programmability. The reason I say programmability is that 5 years back, or even 10 years back, the rate at which these applications were changing was slow. And there were standards. So there was JPEG. So you could go ahead and accelerate JPEG, and it would not change very frequently. There was like H.264, HEVC. It would take a while for like a whole bunch of companies to agree and change that standard, right? Nowadays, we don't have standards, especially because of the application of basic machine learning to everything. So the applications are evolving at an extremely fast pace. And so the future now is about ASICs, but with some sort of programmability so that they can cater to this evolving land of applications. However, you will see specialization. You will see specialization for a class of problems. Image processing pipelines is a class of problems. Neural networks is a class of problems, so that's a class of problems. And you'll also see specialization for platforms. For example, mobile might need a different architecture than cloud, than automotive, than IoT. We may have different energy budget, throughput budget, latency budget, accuracy budget, and so on. So you'll see specialization for different platforms and for different classes of problems. However, even for designing these ASICs with some programmability, the techniques remain the same. Where does the efficiency come from when you're designing these accelerators? Efficiency comes from basically One, modifying the algorithm such that it becomes well-suited for hardware implementation. So when I talk about modifying the algorithm, I talk about all of those techniques that I talked about, like figuring out where sparsity is, figuring out what computation can you remove without really affecting the result, and so on. So modifying the algorithm. And then basically in accelerators, where is the benefit coming from compared to a CPU, right? The benefit is coming from basically reducing or amortizing instruction overhead, basically by doing a lot of work per instruction, both by doing like data parallel stuff and by doing very complex instructions. Like each instruction does a very complex operation. And essentially what I mean is that like in a CPU, when you say add, it'll just add 2 numbers, right? But in my bilateral filter ASIC, I say one instruction, which is filter, and filter is not just an add, filter is like a whole bunch of work, right? So per instruction, per control, I'm doing a lot of work. And data parallelism. So for example, when you say like multiply, I don't do like 1 multiply, I might do like 1,000 multiplies or something. Okay. Something that I didn't really talk about was reducing precision and using the right data encoding. So in all of these accelerators, you don't really work with like 32-bit floating point or even 32-bit integers. You might work with like arbitrary bit widths, 4 bits, 3 bits, 5 bits, and so on. And the advantage of designing these accelerators is that you can work with the bits, the number of bits that are just enough to meet the accuracy that you want to have. Whereas having compute or processors doesn't allow you to do that. And then finally, designing a memory hierarchy that exploits locality. So in both this line buffered pipeline case and the first one, the deblurring case, we had a lot of like on-chip memory that exploited locality, meaning that if the kernel at this point is working on this set of pixels, if I move a little, it's also sort of working on an overlapping set of pixels. So there's locality in my axes. And by using these on-chip caches, I'm exploiting that. So that gives me an energy benefit. Okay? So that being said, there's a bunch of challenges. The first one being designing. So most of these accelerators that I designed required a very deep understanding of the algorithm. Because if you want to know where to cut computation, you better know how cutting that computation is going to affect your algorithm and the final outcome. So it does need a very deep understanding of how the algorithm works. So how do you figure out this algorithm architecture co-design when basically circuit designers have to basically become experts in the algorithm that they're trying to implement? And then so far, I didn't even really talk about the programming model. So when you're doing fixed function accelerators, so all of the accelerators that I described are kind of fixed function accelerators. So it does bilateral filtering. It doesn't do any other kind of filtering. It basically does bilateral filtering, nothing else. So my programming is easy. I just tell it to do bilateral. I'll say, here's the data, here's the image, go bilateral filter. And that's it. So there's not really any programming involved. However, when you start designing these configurable accelerators, then you start running into the programming problem. So for example, all of these neural network accelerators that you have out there are facing this programming problem. How do you program for this, right? Because it's not doing just one thing. It's doing a bunch of different things with some bunch of different parameters. But how do you write a program that exploits that? And then the third key challenge is lowering design costs. So we want to design accelerators. We want to design a lot of them, but designing each one takes a whole bunch of time, effort, and money, right? And so how do you lower design costs? So what am I working on right now? I'm working on basically addressing these problems. So I have been at Stanford for about a month and a half, and I'll give you like a very high-level tour of the things that I'm working on. So the first project that I'm involved in is called Stanford Agile Hardware Project. And essentially, what the project is doing is trying to lower the design costs of designing these specialized accelerators. And I'm working on this with a bunch of different faculty. So there's Mark Horowitz, who you probably know. And then there's a lot of computer science faculty, Pat Hanrahan, Clark Barrett, Kayvon Fatahalian, and a whole bunch of students. And essentially, what we're saying is that if you want to design something, so we established that we don't want to design something for one application. We want to design something that's okay for a class of applications. And so we said, let's just pick an application space. Let's just pick images and video, right? So images and video are typically characterized by lots of parallelism and lots of locality. And you can exploit such parallelism and locality by basically having a sea of processing elements in these tiles that do that processing. So that can work on a lot of pixels in parallel, and then also have some memory on these tiles that can store them locally. For example, memory that can be used to create these line buffers so that you don't have to go back to memory. So we are designing this architecture, which is basically a sea of these tiles, and the tiles can be this processing tile, which you can think of it as like a tiny bare bone processor. And there are memory tiles, which you use to create these line buffers. And that's the chip we taped out. And what we are doing is that we're saying this kind of substrate is good to play with for image processing applications. And what we're doing is that we are building an entire programming toolchain around this architecture. So the goal is to take an application. In this case, it's expressed in this language called Halide, which is a domain-specific language for image processing type of workloads. And essentially, a Halide application looks like a graph of these kernels. So you have an image, you apply some kernel. Kernel could be a convolution, a Gaussian blur, something, right? You apply that kernel, you get another image. You apply another kernel to it. And so your application is basically this graph of kernels on the right. And what we are building is a programming toolchain that takes this application and compiles it down to configuration of this coarse-grained reconfigurable array. So it's similar to programming in FPGA, but programming in FPGA from a higher level language. So from something which is even higher level than C++, all the way down to basically configured coarse-grained reconfigurable array. So basically, this programming toolchain can take this line buffered pipeline DAG of applications and convert it into configuration of this, and then there can be a driver which can run that application on this CGRA in real time, basically. So not only that, not only are we building the substrate and the programming toolchain, we're also working on how do you generate the CGRA? How do you make writing this accelerator productive and easy? So for that, we have another pipeline, which is basically, so the stop thing shouldn't be application Halide, but never mind that. So we're building this pipeline, which is basically a staged generator for generating this coarse-grained reconfigurable array. So basically what we are saying is that instead of making one CGRA with 16 cross 16 tiles, 4 tiles of PEs, rest tiles of memory, instead of fixing this configuration, we let all of this be parameters, right? And so we'll not build a CGRA, we'll build a CGRA generator where you can easily change these parameters and get different hardware out. So hardware for mobile, hardware for IoT, hardware for cloud, based on what these parameters that you set in your generator. And not only that, not only just parameterizing this generator, we are working on automating this entire design toolchain. So for example, we're working on the state generator that takes a logical description of my generator and performs some analysis on it to, for example, figure out what the floor planning should be like, figuring out what the testing collateral should be, figuring out what the physical design collateral should be. So basically automating the whole process from specifying the parameters of this generator all the way to like basically getting layout out of this. And we can talk in more detail about this if you're interested. So what have we done? By combining the programming toolchain with this generator, what it allows us to do is it allows us to do a very rapid design space exploration over a very large set of applications. So now you just don't have a CGRA sitting here which can run the one application you designed it for. You can map any halide application, which is basically any image processing application, onto your hardware. You can see how it performs, and you can change your generator parameters and spit out a new design, which will be more optimized than the previous design. So we can configure how many Ps there are, what are the Ps doing, how much memory there is, etc. So all of these are generator parameters. So combined with software plus the generator, you can basically produce highly optimized designs. Okay. The next project is also very similar. So now instead of just focusing ourselves on the CGRA platform, we are saying that we can basically take any image processing pipeline expressed in halide and basically spit out an ASIC, right? Because why can we do that? Because we know what the template is. So we know that most image processing kernels have this line buffer template. Input image comes in, one kernel gets applied, there's a line buffer, and another kernel gets applied, there's a line buffer, and so on. So they have this template. Similarly, neural networks also have a template. The template is that there is a sea of processing elements or multiply accumulate units, and there are multiple levels of memory hierarchy, and each level of memory hierarchy is a double buffer because you want to hide the amount of the memory write time with the read time, and so you have a template. Once we have a template, we can automatically analyze the code to basically fill that template in with the application at hand. So this project basically focuses on using these templates and basically generating Verilog descriptions of ASICs out, and combined with our physical design toolchain, we can basically spin out a chip from a halide description, given that it corresponds to these templates. Now the challenge is, how do we find these templates? Once you have these templates, how do you analyze a large piece of code and fit which part of your application corresponds to which template? Right? How do you figure out resource allocation between templates? How much area do I assign for my neural network? How much area do I assign for my image processing pipeline, and so on? So these are all questions that we're interested in finding answers to, and we're working on this. And then finally, a side project, I have a couple of students who are co-advised with Professor Philip Wong and Subhashish Mitra. And there we are looking at a different class of applications. So all of these previous applications, they're all compute bound, which is why it makes sense to build accelerators for those, right? If your application is not compute bound, it doesn't make sense to build an accelerator for it because it's memory bound, right? So for memory bound applications, it doesn't make sense to build accelerators. It makes sense to build better memory systems. And so we are figuring out how to make better memory systems. So for example, can you avoid reading out all the data and perform some computation inside the memory? Or can you leverage new technologies like RRAM, which offer very high bandwidth memory that you can access via like some 3D integration? So we are just starting out, and we're in the process of designing accelerator architectures around these new memory technologies. So I'll stop there, and I'll stop at this slide, but I'm happy to take questions. Yes?
Wonderful about multi-purpose programming, engineering, versatility, but the examples that you gave thus far made it sound as if the designs that you ended up were in fact almost totally single-purpose designs. Do you have a way to give a filter that in fact can be used for a variety of things?
Yes.
Second question, let me confess to
Yeah.
character defect. I'm a physicist.
Okay.
And I look at a smartphone as being, in fact, a measuring instrument that's present when whatever is going on is going on. And I say, for God's sakes, why were you so aggressively ignorant as to try to pull the kernel out of the camera part when you've got all these beautiful inertial parts more generally? I look at the camera and I say, well, gee, you've got a bunch of different sensing modalities, and I use data from the others to help me with these things that are actually rather difficult in the imaging. Thank you.
Great questions, and I agree. The examples that I gave in the beginning were indeed fixed function accelerators. They weren't designed to do anything else. So they were doing that one application very efficiently, which was what I did in my PhD. But what I'm saying is that was 7 years ago when I started working on those processors, at which time the landscape was much different. Now the landscape is extremely, like orders of magnitude more rapidly evolving. And so now we don't necessarily want to build fixed function accelerators, and that's why we're working on projects where you can build more configurable, programmable accelerators. And we're tackling the problems of programming them, which is basically the most difficult problem when you have something configurable. The second question, yes, you can indeed use inertial sensors to help you deblur. The problem is that the inertial sensors are not very accurate when you're talking about these camera shake motions. And so if you directly took the motion out of the inertial sensor and used that to deblur your image, you would probably not do a good job. But you can use it to initialize your blur kernel. So that will reduce the number of iterations you spend while doing in your deblurring algorithm to get to the final image. So yes, that can absolutely be done.
Talk to the guy who designed the inertial sensor.
Yes.
You explain to him that you want a better one. He'll probably be so happy to accommodate you quickly.
Actually, you can use measurement to calibrate the inertial system.
Yeah, that's possible.
I wanted to ask you a question regarding your deblur chip that you designed during your PhD. So you talk a whole lot about the algorithmic approach that you use to do the energy saving. What did you do on the circuit side? Did you do anything to enable lowering the voltage, or you did and you chose to skip over it?
Not really. Like most of my focus was on the architecture of the chip itself and on the algorithms and basically how to cut computation. The voltage scaling was basically enabled by whatever voltage scaling the technology allowed me to scale it to. So not really any circuit tricks there. One could apply some, I didn't have the time to do that, but one could apply some sort of power gating to portions of that circuit, because it's sequential. So there are blocks that you only end up using in certain parts of the computation, even though you try to share as much as you can. So some kind of fine-grained power gating would actually lead to saving more energy.
You showed a graph that you were lowering the supply voltage. You never reached near threshold.
But that's because of the memories. Yeah, the SRAM stopped working at way higher voltage.
So I was wondering about your comment about 3D memory. Is it just memory chips that are using 3D techniques, or are you talking about a host processor which is bonded in a 3D way with a memory?
So it's the diagram that I showed is a two-dimensional memory, which is sitting in very close proximity to which you can actually fabricate it on top of silicon. So for example, these RRAM devices, you can have like a layer of RRAM devices on top of a layer of silicon devices with very fine pitch connections between memory and silicon.
Are these two separate dies or wafers that are bonded together?
No, that's one. It's that integration processes.
It's a sequential integration?
Yeah, so you do the silicon and then you grow.
Okay.
Yeah.
I think it's Subhash that's working on that, right?
Yeah, Subhashish and Philip Wong are working on that. I'm working on mostly the architecture side of it. So once you have this memory with very close proximity to silicon, what can you do with it in terms of applications? and architectures.
I have a couple of questions. My name is Nirmal. I did PhD in Stanford 35 years ago. I was a classmate of Mark Horowitz, Gary Browner, etc. I am retired now. So 3 years ago, I was working in Aptina imaging thing. Now it's part of onsemi.
Yeah.
Kind of feel guilty. I think your approach is complementary, but the CMOS image sensors circuits are pretty advanced. Because they're forced to do this. Optical image stabilization was already available in DSLRs, so they're forced to do that one. So usually, you have a floating diffusion, a source follower, and a row selector. But there is also a global shutter in which you can take the frames and a large thing. So for this optical image stabilization, they have some selected rows or columns. I cannot go into the details, but they can turn on those things and they can sample how the motion is going. That's complementary to the initial thing. The second thing is with the LED lighting, right? It is not an analog change. It's actually like a microwave. That's a full power. By the duty cycles, you vary the average power. But unfortunately, the dimming frequency of the LEDs varies depending upon the manufacturer, right? One can select a dimming frequency of 100, somebody can select 1,000. But the CMOS image sensor itself has got an integration time. And if that integration time is not coordinated with this dimming frequency time, then like a strobe, you will be sampling, if I'm waving my hand, at one instant the LED light will be full, and the other instant it is zero, so the image will be automatically be blurred. So you're forced to find out what is the frequency of the LED and synchronize that one.
Got it.
So my question is, when you have so many hardware things that are already being done, right? Are you utilizing that in your approach, or is it you're ignoring all those things and just trying to do everything by algorithms?
Yeah, well, I mean, it depends, right? It depends upon how much of this these new technologies are available in, say, off-the-shelf cameras, right? So, for example, advantage of doing it in computationally is that you can basically use it with any camera.
Second thing is why.
So if you have that, it'll be great.
Second question is, you and Palo Alto and Cupertino, there is a #1 company, right? So their core is, they may have at 7 nanometers, 1,000 cores. They can dedicate 2 cores for your approach. So have you thought about coordinating, because you don't care about implementation, right? Your specialty is in developing that one. If you can do in 40 nanometers, the same thing they can implement in 7, you would care less because that is their choice to implement for lowering the power. So why is not Stanford doing that kind of a thing, working with the industry?
Sorry, why isn't Stanford working more with the industry?
No.
I think Stanford is working.
See, the thing is, you instead of making an ASIC by yourself, okay, you made an ASIC that is a kind of a prototype.
Yeah.
But that may be at 40 nanometers, it's too big a die and everything, right?
Yeah.
So Apple is kind of a general contractor, right? They don't make the CMOS image sensors. They don't make the lenses. Lenses are made in Taiwan. So, your input is, a more intelligent way of implementing that one. So the exact details of implementation probably are not that important as the approach, right? So that's my question.
Well, I mean, we try to work with the industry. I mean, the problem there is like the amount of communication is not equal. Like you end up talking much more about what you do than you hear about what the industry is doing. So you don't get a lot of feedback, depending upon which company it is.
Okay.
So.
Okay.
It varies. The amount of collaboration varies with company to company.
Okay, thank you.
But we do try. So Stanford has a SystemX consortium where we try to bring in companies and match students with companies on particular projects. So.
Okay, thank you.
Yeah.
This deblur was I understand, done over the whole matrix or the whole array of the pixels. Can you localize it to a specific subset?
Yes.
Like if part of the image is blurred?
Yes.
And then a follow-up is kind of what applications would this be used for? I mean, the camera shake was one, but
Yes.
maybe like, I don't know, a security camera sees something walking by really quickly
Yeah.
and it's blurred then.
Yeah, it's a different kind of problem.
Oh, okay.
The problem is that here the assumption was that the entire image is blurred, right? When you have someone moving in front of a security camera, the entire image is not blurred. A portion of it might be blurred. So you might be able to use this approach if you're able to segment out the area that is actually blurred. But in general, it's a different problem. It's called motion blur. And you can't represent it as a convolution, which is like this, applying the spatially invariant kernel. So you could apply parts of the techniques that are used in designing this for motion blur as well, but it's not the same problem. Yeah.
Sake of the recording. What algorithms, what are you thinking about when you're doing this 3D memory structures? Are you thinking about doing in-memory processing, near-memory So what is your high-level thinking?
I think like we are interested in all these kinds of processing. We are at a point where basically just starting out exploring the kind of algorithms that would benefit from it. Like, for example, even in many neural networks, there are certain layers that are compute-bound, and then there are certain layers that are not compute-bound, that are memory-bound. So, for example, fully connected layers are memory-bound. Similarly, RNNs and LSTMs have this matrix vector multiplication, same as fully connected layers, which are memory-bound. So we're looking at these memory-bound applications. Graph analytic applications are memory-bound. So we're basically trying to see we're in the process of identifying applications that would benefit. But if you have ideas about applications that would benefit from this, like we are open to trying them out.
What were the device sizes? You know, you mentioned devices, usually number of transistors, number of gates.
Yeah, a couple of 100K.
If it's 50,000 gates, so maybe it is a coprocessor, you know.
No, it's on the order of like hundreds of thousands or a million even. Well, not just gates, including memory and stuff. Yeah. So the die size is like in 45 nanometers, this was like 2.5 millimeters cross 2.5 millimeters. So like not negligible. Not negligible, but not like humongous either.
For the general hardware project you described, you mentioned FPGA. Like, how is it different from FPGA? Is it just the programming interface? Or
the granularity of the compute, basically. So FPGAs, the interconnect, we're working at a bit level, whereas here we are working at a word level. So for example, a 16-bit word, for example. Also, the kind of processing elements that we are thinking about are more specialized and lookup. So it's similar to the FPGAs in the sense that FPGAs also have like some DSP blocks and some more specialized engines. So you can think of this as an array of specialized engines.
And in your previous project, did you compare the power numbers with any FPGA implementation?
I did not compare, but it was like an order of magnitude higher. Yes.
All right.
Twice, I think your slide showed 2.2 kilojoules to process this on a more or less conventional smartphone. Is that correct?
Yes.
Did you also say that that would deplete the battery?
Well, on an iPhone, I didn't say it would deplete it. I said it would deplete it if you deblur 10 photos. And that was an iPhone 6.
Good.
Yes. Thank you.
moment.
Is there a photo?
Yeah, we'll take a photo. I'd like to invite other societies to come up on this stage and have a final photo with the speaker. Computer Society, Circuits and Systems, and all other sponsors and attendees, if you have questions, you can, speaker will be here for a couple more minutes.